All right, how is everybody today?
Good. Didn't totally bomb my calc quiz, so that's nice.
Excellent. Hey, all you gotta do is survive, right?
That's what I did.
I don't have to do calc 4, so I'm quite pleased by that.
Ah, cool.
Yeah, you're my advisor, you know that.
Yeah, Calc 4 is theoretically optional now, but the alternative to it at WSU is possibly worse than Calc 4. So it may be something you'll want to end up taking anyway. But only has to be done before you graduate from WSU, so lots of time. All right, any questions? All right, well, let's just keep talking more about processes. So we talked a little bit about fork yesterday, and remember, fork is the main way that we create new processes in Unix. And when you call fork, it returns an int, and that return value is the only difference between the original process and the cloned process. All right, everything else about the two processes will be exactly the same. They'll both have the same program in their own copy of memory. Their own values of variables will be the same, and so on and so forth. The only difference is that one of them, this call will return a 0. The other one, it'll return non-zero. The non-zero return, that goes to the parent, and the 0 return is what the child sees.
Is there a way to essentially execute it like a tree thread? Like, I want this thread to spin up and do this bash function, and I want this thread to spin up and do this bash function, and it might target different physical threads on the computer?
So there is. After you do a fork, you're an exact clone, but you can, save your process ID, and then if your process ID is 0, you know you're the child. What you do is you basically change into a new execution context. So there's another function called exec or exec. There's a bunch of different versions of this. Usually it's called exec. And exec basically lets you take your essence and replace it with something different. So first you make yourself a clone, and then you transform yourself into what you want to be. And this is how you create a fundamentally new process. And execl basically takes, an executable file name. And so after I've made myself an exact copy of my parent, now I change myself to be a process that is running some other program from my file system. And now I've got, a separate process running a totally separate set of code that has nothing to do with the original process anymore, except that that was where it came from. So we'll play with execs in a little bit, and they're kind of mysterious, but in a cool sort of way. All right, go ahead and send an attendance note, please. And let's take a look at one more thing before we dig a little deeper into this. So I mentioned if you do ps-e, it shows you information on every process in the system. So let's just do an ELF and see. Everything that's out here running on my laptop. And I've got Thunderbird, my mail client, console. I got code blocks because I'm doing some C++ and all this other stuff. And some of these jobs are owned by me, like OpenCPN, that's a charting package. Some of these jobs are owned by root. And every job you can see who created the job. This is the process ID. This is the parent's process ID. So my XFCE4 session, which is my window manager, is 7654. Its parent is 7526. And if I look through, I can find 7526. That's a thing called SH. That's a different type of shell. And the parent of that is 7501. And 7501 is a process owned by root, which is LightDM, and its parent is 6908. And so you can trace this hierarchy of, where did each process come from? And, we can keep going. 6908 is another LightDM. That was created by process 1. And there's a whole bunch of processes that were created by process 1 or process 2. And if you go up to the top of this and you look at process 1, it's a process called a init. And that's basically where the system begins. The first process that's executed on Unix when you boot up is a init. And it's basically the parent of all other processes, except for this process 2 business, which we won't worry about. But when you boot up, you create an initial process, a init, and then a init will, execute forks and execs to create other processes that are supposed to be running after your system boots. And those other processes will be responsible for creating other processes. And it just kind of builds from there. So if I'm on the Linux server and I look at Nick, right, here's the PS command I just executed, which was process 40039. Its parent was 40017. That's my bash command, right? That's the bash shell that I'm running. And bash was created by process 40012. And 40012 is, guess what, SSHD. That's the daemon or the server process, which is responsible for responding when you try to SSH to the machine. So when I say SSH, the Linux server, I'm actually making a communication channel through something called a socket with a process SSHD.
I have a question.
Yeah.
What exactly is a daemon?
A daemon is basically a server. But it's usually a particular type of server, so it's a process that usually runs forever and waits for requests from other processes and then does something on their behalf. Basically a server. So if we're doing SSH as a client, we connect to something called SSHD, the SSH daemon. If we do HTTP, we connect to a process called HTTPD. That's the web daemon, basically. If you want to do a print command, you'll talk to LPD. That's the daemon for LP, the line printer. And if I look for process 40,001, that's owned by process 791. That's another SSH daemon. And if I look at 791, that is the SSH daemon from user sbin SSHD. It was run with a -D switch, which says act like a daemon, be a server, right? And the parent of this process is 1, that's a init. So this process was created at boot time by the init process because there's a set of instructions that basically say, hey, when you log in, we should start, something that lets people SSH. And then that SSH daemon created this process when I tried to make an SSH connection.
Who server is this? This is the school server, or is this your personal server?
Are you on the Linux server?
The Linux.exe.
and there's a spool server.
Well, I'm asking, is this server running at your house, or is
No, this is somewhere in Pennsylvania. I think it's a virtual machine.
Oh,
It's a service I pay $10 a month for, and they take care of it for me.
oh, okay.
Yeah, I actually have no idea like what the actual physical machine is. You can, see it's an x86 machine, but I don't know much else about it. But I can go through a web page and I can reboot it and stuff like that.
I thought it was on campus at Park, or is that CTEC?
That's the CTEC server. And for this class, it seemed useful to be able to do things like, reboot the server if I want, or add accounts myself, or things like that. So we have our own server for the CS series. But if you ran your own server, at your house, it would look exactly the same. And if you have an SSH daemon running, then you can make SSH connections to it. And I don't have that running on my laptop because I don't want to be able to SSH into my laptop. It's just a little more secure if I don't have that enabled. So yeah, so you can see the process tree and sort of work backwards through time and kind of figure out where all of these things came from. Can you explain to me who is root? So root is the system user, the super user. Anytime that you want to be able to do something and disregard protections on files, you need to be user ID 1, who is the root. Root used to be an actual login. You could log in as user ID root, put in the password, and you'd be running as root. That's usually disabled now on most systems because it's a big potential security risk. But user ID 1 is still root.
You can still SU root.
But you can still SU root, which says pretend that I'm the user root. SU is switch user. And if you have the root password to execute that command, you can act as if you're root. But root is, it's user ID 0. But there's no login enabled for that. All right, so let's see, where does this leave us? So when you execute a fork, right, you make a clone of the current process, and that's not always terribly useful. Sometimes it is. Sometimes you want to do some processing in a piece of code, and you want to split that processing into multiple threads, multiple processes, to distribute the workload. But a lot of times what we want to do is we want to just run a different program from inside one program. Now in Bash, this is easy to do. If I have a Bash script and I just write a line that says date, it will run the date command. And that's useful. But we can also do this from a C program. And so, for example, let's make an S test. So there's a system call, a function named system, and system basically takes a string, which is a command, and it will execute that command using the Bourne shell. And so I can do something like this. Alright, so I'm going to say the date is, and then I'm going to say system quote date. And that's going to run the date command. And the output of it will just, sort of spill over onto my display, and so this should say the date is and show me what the date is. so if I run that, right, it said Wednesday, December 1st, the date is, and then it came back to my prompt. So almost what we expected. Let me make a small change. Let me say the date is followed by a new line and then run the system command. And now it says the date is Wednesday, December 1st. Alright, so two things we can talk about here. The first is just the simple fact that this is running a bash command basically. It's not really bash, but you know, it's running a command. It's executing a different file on the system called date. Yeah, so I think it returns the exit status of the command.
So when you do that system date, it'll like print it to the screen?
Yeah, it prints it to the screen because that's what date does by default. If the call succeeds, then the return value of system will be whatever the shell terminated with. So typically a 0.
Something like you know, tr said, and then put a variable in there, or is that a little too much?
So yeah, let's build up to that. Because that's what we want to be able to do. If we just have a command, we just want to run it and be done, right? We can just use system. It's sort of a quick and easy. And so this says the date is, and there's the date, and it says goodbye. But let me go back to what we had a moment earlier, which is where I said the date is, and I just take out that new line in the beginning. And it does something very different, right? It shows me the date, and then it says the date is goodbye. So why would it be doing that? Why is this doing such a different thing?
Is the system being executed before it's compiled?
It's being executed after the printf statement, actually. So the printf will happen first, and then it executes date. Say again?
The system runs quicker than the printf does? No, that wouldn't.
That could be. I don't think that's what's actually going on, but that is possible. But this instruction should completely finish before this instruction starts.
Right. So that weird little, is that a space? I don't, sorry.
That's a space in there, yeah.
Oh, okay.
So this is something that can trip you up when you're debugging. And it's pretty subtle, but it has to do with the idea that in a lot of stuff that we do, output is buffered. Meaning, when you try to print something to the screen, it does not print right away. Because printing is pretty inefficient. Sending something to the display is inefficient. And so when you try to print something, it prints into memory first. And the operating system holds it in memory and remembers, okay, you wanted to print out an uppercase T. And you wanted to print out a lowercase h and a lowercase e and a space. And all of this does not cause anything to appear on my screen. It remembers, hey, you wanted to say the date is, but it doesn't actually print it yet. If I put a new line, that by default says, okay, go ahead and everything that the person said they want to print, go ahead and actually print it now. So this is buffered output. And the stuff we're printing goes into a holding buffer. If I print a new line, then the buffer gets flushed, and it actually appears, and we get what we expected. The date is, and then we run the system command and we see the date. But without that new line and without anything else, this print is kind of invisible at this point. And it doesn't actually appear until our program exits. Because this also gets buffered, and then when our program exits, it says, okay, flush out anything that we were supposed to print, and let the person see it now, and says the date is goodbye. But this system, this is a separate process. This is running in its own shell, And when that command is done, it will flush out all of its output. And so you see this output before you see that. And that will seriously trip you up when you're debugging code with threads or multiple processes. Because, you know, it's pretty obvious, since this is printing out the date, that it ran right here. But if I had a print message here to tell me that it was at this point in the program, I might not see that print message till after this happens. And now, you know, your favorite debugging tool, which is just to add a bunch of prints to your program, is working against you. So anytime you're doing debugging, right, always make sure you have a new line at the end of your debug messages. That's going to save you a lot of lost time somewhere down the road, if you remember it. All right, so this system command can do all sorts of things. We could use the ls command, and it shows me what's in my current directory. I can do a print working directory, and it'll show me my current directory, and then do an ls. I could say, let's print our current directory, and then let's change directory to /etc, and let's print the directory again, and then let's do an ls. And so I started off in my home directory, I changed to etc, I printed my directory, that's what it gave me, and then I did an ls. This is the contents of the /etc directory. So let's do a PS. And let's see what's going on while the system command is executing. We're going to need a bigger window. Alright, here's the bash shell. That's the thing that I logged in with at 10:15. And that 864 is the parent of stest. That's the C program that I just began to execute. stest 682 is the parent of another shell called sh. And sh was run with some switches after it, sh-c, ps-lf. Well, if I just say sh, I basically just start an instance of the Bourne shell. But if I say sh-c, that says, hey, use the Bourne shell to execute this command. And so the Bourne shell 683 is the parent of another process, 684, whose job was to execute the PS. And that was the process that was running when this output was produced. If I do a PS right now, all I've got is my bash and the PS that I just ran. And if I run stest again, the bash ID is the same. The stest ID is new, and so is this and this. So this is a really quick and easy way to create processes. And since we're executing this under a shell, we can do things like put in wildcards. So I can list every file in the etc directory that contains an S. And so there's every file in every subdirectory in etc that contains an S. All right, so that's the system command. But let's say we wanted to use tr to translate something from lowercase to uppercase. This is not going to be very satisfying. right? So I'm running TR right now, and TR is trying to read standard in. So I can say hello and it prints out hello and so on and so forth. But I'm not executing my program right now. I'm inside this call. I haven't said goodbye yet. And so TR is running, and if I hit a Control D, TR will execute, will exit. But let me just do a PS-L right now. Right, so there's my bash, there's stest. Stest is the parent of this thing, which is saying do a shell with the TR command, and here's the actual TR command. And when I type here, I'm not feeding input to my program, my stest. I'm feeding program to TR. And when I hit a Control D, then this system call returns, and it says goodbye. But here's what I'd like to do. I'd like to write a loop in C that will read, wow, I'm like all over the place here, that will read, one line at a time from standard in, and then use TR to translate it to uppercase. And that's not what this is going to do. If I say hello, nothing happens, right? There's some flashbacks here probably to PA5, right? When I said hello, that was feeding the input of this fgets call. And now I've come back from fgets, I've saved hello in buffer, but now I'm executing the system call to TR. And I'm stuck in the system call until I hit a Control D. And now I'm back at my call to fgets. And now I'm back to my call to TR, and so this will read standard in and send it to standard out. And when I hit a Control D, I'm back in my call to fgets. And if I hit Control D again, fgets will notice end of file, and that'll kick me out of my loop. So this is not optimal, right? System really kind of disconnects from the main program. It stops your main program and you go off and you execute this command. And it's really just kind of like, you're doing some task and you've got an assistant and you turn to your assistant and you say, hey, go take care of such and such. And there's no way that you can talk to your assistant once they've left to do this task. They're going to go off and do this task and you're going to take a nap until they come back. And so if you just want them to print the date or delete a file or something like that or clear the screen, that's easy. But if you want to interact with them somehow, if you want to give TR a string and have it convert it, we need something more finessed than just system. We need a way to send information to this process once we've created it. And so this is where we talk about popen. And so we know about fopen. This is how we open a file. Popen is the same calling structure. We have a file name, and then we have a mode. And it returns some sort of file pointer. If we do an fopen, this opens the file, and if we say quote W for write, then we can write into fp with an fprintf, and whatever we write will get stuffed into this file. With a popen, this is actually a command. And if our mode is write, quote W, what popen does is it begins to execute this command, but it connects standard in to this file pointer. So anything I write into this file pointer feeds standard in of this running command. And if I open it for reading, then it connects standard out of this command to the file pointer. Anytime I read from this file pointer, I'll be reading whatever this command sends to standard out. So with popen, I can begin a process executing, and I can either read its output or I can supply its input from my program by using this file pointer. And so this is a high-level function. So it's in chapter 3 of the manual pages. And takes a command, takes a type, which is usually read or write, and it returns a file pointer. And when we're done with it, we can call pclose, just like we call fclose to close a file. And it creates a pipe, forks, invokes the shell, and then executes the command with standard in or standard out connected. All right, so let's play with this. So we'll use FP to write to standard in of the command. So we're going to create a process that's running the tr command. And I'm going to have this file pointer fp, which I can use to send information to this process while it's running. So I'll read a line from standard in, and then I'm just going to say fprintf fp %s, and I'll just write out whatever the user typed. And so I can say this is a test, hello, weird, Control D, and I get my uppercase output suddenly. But I really wanted to type hello and have it say hello, and type this is a test, and have it type this is a test, and so on. And again, we're dealing with buffering here. Right? When I do an fprintf to this pipe, it does not get sent immediately. Even though there's a new line at the end here, when we write into a pipe's input, that write is buffered. And if I want to force it to write, I have to use fflush. And fflush is another one of these things that will save you a lot of hair pulling late at night. fflush says, hey, whatever's been sent to this file, fp, go ahead and force it out. Make sure it actually gets sent wherever it's going. If this is a file on disk, it will actually write it to the disk. If it's a process, it will actually send it to the process. And since my input ends with a new line, when tr gets this set of characters that ends with a new line, it should immediately convert those characters according to this translation and send the output to standard out. So now if I run this, I can say this is a test, and I immediately see the output. And then when I hit a Control D, what happens? My fget returns null. I kick out of here. I say goodbye. I exit. When I exit, this process will also exit. But if I wanted to be really clean about this, I could do a pclose on fp to shut down the process. All right, So that's how we can use popen to start a process and feed information to it. We can also open a process and read information from it. So suppose I wanted to read a list of files inside a C program. So I'm going to do this, fp equals fopen, ls read. Alright, so I'm going to do the following. I'm going to count how many files I have in my current directory, and I'm going to do an fgets, but instead of reading from standard in, I'm going to read from fp. Alright, going to open a pipe to the ls command. I'm going to open it for reading, so when I read from fp, I'll be reading whatever this command sends to standard out. ls should produce on standard out a list of files, one per line. And so now I'm going to have a while loop that basically reads one line at a time from that file pointer, fp, which is the output. So each time through this loop, buffer should be the name of the next file in the list that ls produced, and I'm just going to print that out. I'm going to print out a file number starting from 0, incremented after I print it. So I'll say file 0 and show the name of the first file, file 1, show the name of the second file, and so on. And so I've got a C program that is accessing information about the list of files that are in the current directory. And that's a pretty cool thing to be able to do. If I wanted to find more information, I could do an ls-l. And now I'm not just finding the file name, but I'm finding the whole ls line. And then if I wanted to do something more with that, I could, break that out inside my C code and, parse it using scanf or whatever I wanted to do. But the point is I'm using another program inside the C program. And I'm not just running that program, I'm actually capturing its output. So you may be getting some ideas for things you could do with this. And it's a pretty powerful capability. So questions so far?
Is this going to be on the final?
Sure, why not?
Sorry, what was that? I was away for a sec. What did you say?
Someone asked if this was going to be on the final, and I said, sure, why not?
Oh.
I'm going with regret for even asking that question now.
Oh, well, I mean, so ask questions about what we're doing, for sure. I'll give you a study guide by Friday that will list, the things that I would like you to know. And I don't expect you to know, everything about processes after 1 week of lecture on them, and no programming assignments on them. But, low-hanging fruit, right? You should know the idea of the fork statement and the fact that fork clones a process and that the return value lets you know if you're the child or the parent. And that's probably all you need to know about fork. You should know that system lets you execute a command, but that you can't interact with the program that's being executed by system. You should probably know that popen is a way that you can execute a command and either send to it or read from it. And we're going to talk about exec, and you should know that exec will be a way to change your current self into a different process. And that ps is a command for looking at processes, Control-Z suspends, Control-C interrupts, BG and FG take a suspended process and run it in the background or foreground. Kill lets you send a signal. So I mean, there's concepts here that that you should at least have heard and you know, be able to match in a multiple choice or a fill in the blank kind of thing. But I'm not going to ask you to write code that, you know, uses popens or things like that.
Thank goodness.
Yeah. So here's a little bit more extreme example of using popen. So so we know the program BC, right? BC is our calculator, and you know, it lets you type in expressions, and it gives you the return value. It's the thing I always use in 215 when I'm trying to do exponents and stuff. So here's a file called C3, and it basically it does a popen on the BC command, and it opens it for writing, so it lets me send information to this program. So I'll put a print statement saying I'm going to execute popen, I'll call the popen, and I'll come back and print out the value of FP when I get back, just to see what popen returned, and it should be something non-zero. And then I'm going to do a series of writes. I'm going to write out 2 + 3 \n, 5*9 \n, and this big long expression \n, and I'll flush FP. And then I'll wait for the user to type in an enter key, and then I'll close my file pointer. And so if I do this, right, it outputs, you know, the BC command runs, and I get these values back from it. And if I do a PS, I can see a bunch of things going on right now. There's my bash shell, there's my C3 command, it creates a shell, it created BC, and I'm running a different BC. Right, so same thing, here's my bash shell, here's C3, C3 is the parent of this shell, which is executing the BC command. There's the BC command, which was executing, which produced these outputs. This was the value of FP that I got back from popen. So popen is useful for doing sort of one-way communication with a process. I want to run BC and I just want to give it instructions, and I'm going to let its output go to standard out. Or I'm going to run the date command and I just want to capture what the current date is. And so I could run date with a popen with a read modifier, and then the output that it produces, which is the date and time, would be available to me by reading, you know, with an fgets from that file pointer that I got back from popen. But a lot of times what we really want is two-way communication. So I want to run a main program, and at some point I want to create a second process, and I want to be able to write to standard in of that process and read from standard out of that process. And that's a lot trickier. System is great if I don't want to do any communication with the process. popen is great if I want to just write or just read. If I want to do two-way communication, I have to wire that up myself. And that gets pretty complex pretty quickly. And to do that, I need to get into this business of exec. And we got about 3 minutes, so I can start this. So execl is low level. It's oh, actually it's high level. It's chapter. It's chapter 3. Interesting. And this is a mysterious function. Okay, so the description, these functions replace the current process image with a new process image. All right, fork creates a clone of the parent in a child. Exec replaces sort of the essence of that clone with something else. And it causes that process to begin executing different code. So let's take a look at this.
Wait, so you said that Excel replaces what?
Replaces itself.
Okay, and then fork is just cloning it to make a child, right?
Fork creates a clone. Exec executes a... So fork will create a clone. Exec will replace the currently running process with the code from some other file.
Okay, thanks.
So if we ignore fork for a moment, we just look at this, it's a 2-line program. The first line says exec v bin/ls. And the second line is a print message which says you'll never see this. So what's going to happen when we run this program is this will say, hey, let's find the binary code inside this file. Let's replace ourselves with that code. And after we come back from this, we're no longer running this program, which means this print statement never gets executed. But this statement will execute because the code inside gogo.c has been replaced by the code inside /bin/ls. So if I run gogo, I get an ls command and I never see this print statement. And so if we wanted to execute ls as a separate process, we would basically do a fork first, and then maybe have the child execute this. So the child basically becomes /bin/ls, and the parent can continue doing its thing. All right, so we'll talk a little more about this tomorrow. Let's see, is this covered in 222, 223? So 223, we'll talk about threads and processes in that context. 222, we probably won't do this, but you'll do a ton of this at a university. When you get into a system programming course, you'll be doing this. So this is really just kind of first exposure to it. But we'll talk a little more about this tomorrow, and we'll call it good after that and start talking about final exam. Probably later tomorrow and definitely on Friday. All right, send me an attendance note, please, and I will see everybody next time.